Hello everyone, welcome back to the channel. In this video, we are going to discuss a GATE 2025 linear algebra problem and its complete solution. After that, we will see the core concepts involved behind the above problem. And finally, we will solve a few practice problems plus some problems for you to try yourself. So, let's begin. So the problem is, let x1, x2, xn be a set of linearly independent vectors in Rn. Let the ijth element of matrix A, which is an n cross n matrix, be given by Aij is ijth element. Ijth element of A is equal to xi transpose into xj, whereas ij is in between 1 to n. We need to find which of the following statement is correct. A is invertible, 0 is a singular value of A, determinant of A is 0, and Z transpose Z is equal to 0 for some non-zero Z which belongs to Rn. Okay, so let's moving on to the solution. What we have is, we have given that A is an n cross n matrix such that ijth element of A is equal to xi transpose into xj, and this set which consists of x1 x2 xn is a linearly independent set. Okay, so first if we carefully see this A matrix, okay, whose ijth element is xi transpose xj, okay, if we carefully see this A matrix, then this A matrix can be written as a11 a12 a1n, similarly a21 a22 a2n, an1 ann. Okay, where if we see this element a11, a11 is nothing but x1 transpose into x1. Okay, x1 transpose into x1. Similarly, a12 is x1 transpose into x2. A1n is x1 transpose into xn. Similarly, if we see an1, which is xn transpose into x1, ann is xn transpose into xn. This can be written. Okay, so if we carefully see this matrix, this is nothing but A is equal to, this can be written as x1 transpose multiply with x1 x2 xn. Similarly, x2 transpose multiply with x1 xn, and similarly. Okay, so taking the this is equal to xn transpose into x1 up to xn. So if we take this term as common, this term out, then what we'll get is, we'll get x1 x2 x1 transpose x2 transpose xn transpose into this x1 x2 xn matrix. How? Because if we multiply this x1 transpose x1, x1 transpose x2, x1 transpose x1, this will be the first row of A. Similarly, if we multiply xn with this, we will get the last row of A. Okay, so we will get A is equal to this into this. Now if we see, let we assume this capital X is equal to this matrix, which is consists of x1 which consists of x1 x2 xn as columns of this matrix. Okay, then this is x, and this can be written as x transpose. Okay, so we can see this A can be written as x transpose into x. Okay, now we have assumed that capital X is equal to x1 x2 xn, which is an n cross n matrix, because this each belongs to Rn. Okay, and we have given that this set x1 x2 xn is linearly independent set, which means all the columns of this matrix X is linearly independent. All the columns are linearly independent. Okay, and hence we can say that rank of X is equal to n, because all columns are linearly independent. All columns are linearly independent columns. Okay, this is correct. Now there is a note: for any matrix, whether it is a square or any rectangular matrix, we a rank of A and A transpose is always the same, which means for any matrix, rank of A is equal to rank of A transpose A. This is why, which we will see, this is because the null space of A and A transpose is always the same. Okay, this is one way of seeing how rank of A is equal to rank of A transpose A, because their null space are same. How we can say that? Let's say this is y, because let's say x belongs to null space of A transpose A. Okay, which means if x belongs to null space of A transpose A, it means A transpose A into x is equal to 0, and this is the A transpose A into x is equal to 0. We multiply both sides with x transpose, then this is nothing but 0 only, and this will become x transpose A transpose A into x. Okay, but this term can be written as A into x transpose. Okay, then into Ax is equal to 0. This is this term. Okay, x transpose x, this can be written as norm of x square. Okay, so this is that Ax square is equal to 0, which indicates that Ax is equal to 0, which means x belongs to null space of A also. X belongs to null space of A, and hence we can say that null space of A transpose A is a subset of null space of A. Okay, this can be said. Now second, let assume that x belong to null space of A, and we will show that x also belongs to null space of A transpose A. Okay, so how we can show that? If x belongs to null space of A, then Ax is equal to 0. If we multiply both sides with A transpose, then this is nothing but A transpose Ax is equal to 0. So here A transpose Ax is equal to 0, which means x belong to null space of A transpose A. X belong to null space of A transpose A, which means null space of A is a subset of null space of A transpose A. Okay. From first equation we got that null space of A transpose A is a subset of null space of A, and here we will get the opposite. Null space of A is a subset of null space of A transpose, which means the null space of A transpose and null space of A both are same, which means if x belong to null space of A, then also x belong to null space of if x belong to null space of A transpose A, then x also belongs to null space of A, and similarly vice versa. We can hence the null space of which will hence we will get null space of A transpose A is equal to null space of A. Okay, and we know that what is nullity? Nullity is nothing but the dimension of null space, and dimension of null space is nothing but nullity. Since both the null space of A transpose A and A is same, which and hence the nullity of A and A transpose A is same. Okay, because null space of A transpose A and A is same. Okay, since the nullity of A and A transpose A is same, and hence from the rank nullity theorem we have what we get, rank plus nullity is equal to dimension. Okay, or number of columns if the matrix, if A is a rectangular matrix. Okay, and here we have, since the nullity of A and A transpose A is same. Okay, rank plus nullity is equal to number of columns. Okay, or dimension. Since the nullity is same, and it indicates as rank of A and A transpose A is also same. Rank of A and A transpose A is also same, because the dimension of number of columns of A is same as A transpose A, and hence the rank of A and A transpose A is also the same. Okay, now we have shown that rank of A and rank of A transpose A, rank of A transpose A is always same whether A is a square or rectangular matrix. Okay, so now where we have taken that capital X is equal to this matrix, and rank of capital X is equal to, and because this all the columns are linearly independent. Okay, and A is equal to X transpose X. Okay, so and now we have rank of X is equal to n, and we know that rank of A and A transpose is also the same, which means rank of X and rank of X transpose X is also the same, both is equal to n. Okay, since X transpose X, this is nothing but A, so we get the rank of matrix A is equal to n. Okay, and A is which matrix? A is this matrix, such that ijth element is Xi transpose into Xj. Okay, and we got the rank of a matrix A is n, which is a full rank matrix. Since we have the rank of A is n, which is a full this is full rank, which means the determinant of A is not equal to 0. Okay, and hence what we'll get is we'll get the determinant of A is not equal to 0 because A is full rank and all the columns of A are linearly independent. Okay, since determinant of A is not equal to 0, uh, which also indicates that there is no zero eigenvalue, no zero eigenvalue not is equal to 0, and hence we can get A is a invertible matrix. Okay, so the option A, which is A is invertible, this is correct. And now we have to check the option B, which is 0 is a singular value of A. Okay, first we will see what is a singular value, then we'll see whether 0 is a singular value of A or not. So singular values of A are the square roots of eigenvalues of A transpose A. Okay, if we need to find the singular value of A, then what we'll do is we'll find the eigenvalue of A transpose A and we'll take a square root of this. This is nothing but singular value of A. Singular value of A. Okay, so we know that the rank of A is equal to n. We have seen because A is invertible. We have seen, and we know that rank of A and rank of A transpose A both are always same. So here rank of A is equal to n, and hence the rank of A transpose A is also equal to n. Now A is an n cross n matrix, and this is also n cross n matrix, which means A transpose A is a full rank matrix. Okay, A transpose is a full rank matrix, and hence we can say that the determinant of A transpose is not equal to 0, which means A transpose A do not have zero eigenvalue. A transpose A has no zero eigenvalues, and hence we can say that if A transpose A has no zero eigenvalues, which means A has no zero singular values, because singular value is nothing but square root of eigenvalues of A transpose A. This is eigen singular value of A. Okay, since this eigenvalue is not equal to 0, hence singular value is not equal to 0. So what we'll get is 0 is a singular value of A. This is wrong. Third one is determinant of A is 0. Yeah, and this is also wrong because we have seen determinant of A is not equal to 0. Okay. Fourth one is Z transpose AZ is equal to 0 for some non-zero Z, which belongs to Rn. So now we see whether this is true or not. So we have to find whether Z transpose AZ is equal to 0 for some non-zero Z. Okay, Z is an Rn vector. So we know that A can be written as X transpose X, where X is nothing but this matrix X1 ordered Xn, X non-zero matrix. No, so Z transpose AZ can be written as, if we put X transpose AZ in place of A, then we get Z transpose X into Z. Okay, so if we see this term can be written as Z transpose XZ. Okay, this can be written as XZ transpose into XZ. This is nothing but X transpose X transpose norm of X ka square. This is nothing but norm of XZ ka square. This is always greater than 0 because X is, all the columns of X are linearly independent columns, which means no linear combination of columns of X will become 0. Okay, and Z is non-zero, so this is always greater than 0. Okay, this is always greater than 0, which means Z transpose AZ is always greater than 0 if Z is not equal to 0, and hence this statement is also incorrect. Now moving on to the core concepts that are involved behind the problem. So first one is, let's say we have a matrix A such that ijth element of matrix A can be written as xi transpose into xj, that is inner product of xi and xj. Okay, when I and j varies from 1 to n. So this we have seen this, if ijth element can be written as xi transpose xj, then the matrix A can be written as x transpose x, where capital X is the matrix whose columns are x1 or xn. Okay, this we are already seen. Okay, but if A can be written as into this form, A is such that A can be written as x transpose x, then A is always a symmetric matrix, that is A is equal to A transpose. Okay, so first one is A is always symmetric, that is A is equal to A transpose, Why? Because let's say A is equal to x transpose x. If we take this A transpose, okay, then we can write it A transpose x transpose x square, and we know that AB transpose is nothing but B transpose A transpose. So this will become x transpose into x transpose ka transpose. So A transpose will be x transpose into x transpose ka transpose. So we know that the transpose will become x only. Okay. So this will become x transpose x, nothing but A. So if A can be written into this form, A is x transpose x, then A transpose is equal to A, which means A is always symmetric matrix. Okay. Second one is matrix A and A transpose A always have the same rank. Why? Because we have seen the null space of A and null space of A transpose A. That is, if AV is equal to 0, then this indicates that A transpose AV is also equal to 0. Or if A transpose AV is equal to 0, this means AV is also equal to 0, which means the null space of A and null space of A transpose A both are same. If since the null space are same, which means using rank neutrality theorem, rank of A is always equal to rank of A transpose A. Okay. Now third one is singular values of A are the square roots of eigenvalues of A transpose A. What does that mean? That mean is if we need to find the singular value of matrix A, so first what we'll do, we'll find the eigenvalues of A transpose A and just take the square root. So square root of eigenvalues of A transpose A is the singular value of A. Okay. Fourth one, and these are positive semi-definite. These are the characteristic of matrix. Okay. So first one is a real matrix A is positive semi-definite if A is symmetric and x transpose AX is greater than is or equal to 0 for all x belong to Rn. Okay. That is the matrix a real matrix. A real matrix A is positive semi-definite if A is symmetric, and this term x transpose AX is greater than or equal to 0. And a complex matrix A is positive semi-definite if A is Hermitian or and x transpose AX is greater than or equal to 0 for all x belong to R. Which means if a matrix satisfies these two properties for these two properties and A is real, and then it can be called as A is positive semi-definite. And for a complex matrix, for A to be positive semi-definite, these two properties must be satisfied. Okay. And one more beautiful concept of matrix is positive definiteness. So a real matrix is positive definite if A is symmetric and x transpose AX is greater than 0 for all x belong to Rn such that x is non-zero. Previously, if x transpose AX is greater than or equal to 0, and this is the positive semi-definite property. But in positive definite, x transpose AX must be greater than 0 always, where x is non-zero. And a complex matrix A is positive definite if A is Hermitian and x transpose AX is greater than 0 for all x belong to Rn and x is non-zero. Okay. If the matrix is positive semi-definite or positive definite, then the matrix provides some beautiful characteristics which we are going to see. Okay. So next one is if A can be written as this form, A is equal to x transpose x, then A is always positive semi-definite. Okay, this is the important thing. If A can be written as x transpose x, then this matrix A is always positive semi-definite. Why? Because as we have seen, if A can be written as x transpose x, then A is symmetric. Okay, A is equal to A transpose. Now we need to check whether x transpose AX is always greater than or equal to 0 or not. Okay, so if we see x transpose AX, so A we know that A can be replaced by x transpose x. So x transpose this A into x. So this can be written as capital X is to small x ka transpose capital X into small x. Okay, this can be written as this. This is nothing but the norm of capital X into small x ka square. Okay, since it is a square, it is always greater than or equal to 0, which means x transpose AX is always greater than or equal to 0 if A can be written as x transpose x, and hence this property, this is also satisfied. So A is symmetric, as we have seen, A is symmetric and x transpose AX is greater than 0, which means A is positive semi-definite matrix. Okay. Another one, if A can be written as x transpose x, then A is positive definite when the columns of X are linearly independent. Okay, so if A can be written as X transpose X, irrespective of columns of X are linearly independent or not, A is always positive semi-definite. Okay, but A is positive definite only when the columns of X are linearly independent. Why? Because, okay, so we have seen X transpose AX is always greater than or equal to 0 if A can be written as X transpose X. Okay, this we have already seen. So if the columns of X are linearly independent, then this capital into small x, this can be seen as a linear combination of columns of X. Okay, just taking the linear combination of columns of X, since X is linearly independent and hence linear combination of columns of X will never be 0, will never not be equal to 0, and X is non-zero. X is non-zero, as we are already seen, X is non-zero, and hence this term will never be 0, it is always greater than 0. Hence what we'll get is, if A is equal to X transpose X, then A is positive definite when the columns of X are linearly independent. Okay, and these are some properties of positive semi-definite matrices, which are: first, it must be symmetric. All eigenvalues of this matrix are either greater than or equal to 0. Determinant must be greater than or equal to 0. Trace must be greater than or equal to 0. And X transpose Ax is greater than or equal to 0. Okay. And some properties of positive definite matrix, which are: it must be symmetric. Okay. All eigenvalue is greater than 0. Which means there is no eigenvalue which is equal to 0. No eigenvalue is equal to 0, and hence the matrix is invertible. Okay, always invertible. Determinant always greater than 0. Trace is always greater than 0, and X transpose X also greater than 0. Now moving on to some practice problems related to the concepts that we have seen. So first one is: let u1, u2, un, this set be a set of orthonormal vectors. Okay, these vectors are orthonormal vectors in Rn. Let a matrix A, which is a real matrix and defined such that ijth element of A is the inner product of ui and uj, that this can be written as ui transpose uj. Okay, we need to find which of the following statements are correct. Determinant of A is 0. A is a diagonal matrix. A is positive definite. 0 is a singular value of A. Okay, so the correct option are B and C. So the hint is, as we have seen, as we have solved the previous question, that is, first from this matrix A. Okay, first from this matrix, and then use the orthonormal vectors. Use the orthonormality condition of this set. Okay, then you will get first form matrix, and these use orthonormality condition. Then we will get to know what is the solution. Okay. Correct option are B and C. Second one is: which of the following is true for all inner product matrices A, which is a real matrix, such that Aij is equal to Ui and Uj inner product. Okay. Now we need to find whether A is symmetric and PSD, A is diagonal and positive definite, A is invertible and symmetric, A is orthogonal. We need to find which of the following statement is correct. The same thing. First form this matrix. Okay, form this matrix, and okay, and this matrix will be in form of some u transpose u. Okay, this is what, as we have seen, this if a matrix is in form of u transpose u, it is always symmetric. It is always symmetric and positive semi definite, we have already seen. So A is symmetric and positive semi definite, this is correct. Third one is: let u1, u2, un be a set of orthogonal vectors in Rn. Okay, now this set is an orthogonal set. Okay, this is very important thing. Let a matrix A, real matrix, such that Aij is equal to ui into uj dot product, ui uj dot product. Not sorry. Aij is equal to inner product of ui and uj. We need to find which of the following statement is correct. Okay. A is an identity matrix. A is a diagonal matrix. A is symmetric but not necessarily diagonal. It might be necessarily diagonal. A may have non-zero off diagonal entries. Okay, so the hint is: first form the matrix A, which must be look like u1 transpose u1, u1 transpose u2 and or so on, and use the orthogonality condition of ui comma uj. Okay, then we'll get to know that the option B is correct. Okay, thank you. If you have any doubts or queries, let me know in the comment section below. You can also join our Telegram channel for the discussion or to ask any doubts directly. And for more such content, don't forget to subscribe. Thank you.